Hello. So this is another episode of Ben Talks. I don't know what I want to call this. So today I'm going to be mentioning a little bit about basically what it means to be fast on a bike. What it takes to be fast on a bicycle. So first off, let's talk a little bit in reference to what is fast, all right? So what is fast? Fast is basically getting the farthest distance and the or any kind of distance in less time. Okay? And the better endurance road cyclist you are, the better you can do farther and farther distances with less and less time. So, legitimately speaking, you can't really be considered um, fast until you're able to do an average speed of 20 miles per hour or faster. So, for what distance you do that, though, is going to change. And for there's a lot of differences in terrain and whatnot as well, differences in altitude. So, all these things mean that your average speed isn't necessarily the best way to compare yourself to other people. It's a great tool to compare yourself to yourself, though, because you're on the same bicycle. Okay? You're in relatively the same position on the bike, depending on how much distance you have. The shorter the distance, the more aerodynamic position you can hold with your body's flexibility without your lower body going anaerobic. In other words, your upper body needs to be anaerobic. And this isn't talked about much, but your triceps and your shoulders and stuff have to go into an anaerobic workout when supporting your lower body in an aerodynamic position sometimes. And whether or not you're one of those riders where your upper body has to do that depends on multiple factors. I am, and that really helps my speed when I'm going on lower distance rides. So when you're trying to ride faster, your body is overcoming a few different problems. And that's what I'm going to talk about mostly today. So you hear the biggest thing as being air resistance, but even though that's normally true, obviously it's not always true because sometimes that's taken out of the picture through drafting. So I'm going to talk about the different resistances that you have on a bike. These are going to be in estimated order, and this order changes because some of these resistance is met in a linear proportion. Others are met at an exponential proportion. And we'll get into the math just a little bit. I'm not going to use specific figures. I'm going to use units instead of actual real units. So, let's begin. The first force that you have to overcome is drivetrain friction. Alright? And that drivetrain friction is going to be pretty minimal. In a chain drive system, which is the most efficient, most advanced system that we have for cycling, well, it's the most efficient. Maybe it's not the most advanced, but it's definitely going to be the most efficient. And the reason is there's no friction in the chain. There is, but there also isn't. It's not it's not solid on solid rubbing friction. Okay, it's not doing this. Okay, it's rolling. All right, all the pivots in the chain are actually rolling. Okay, and they're pivoting on washers that are on every single length of the chain. So you have to understand that that's not real solid on solid friction. That's actually fluid friction because it's only friction between the fluid that's within the actual gear parts. So that's what that little piece is in between in between the metal links of the chain. So there's no friction there, all right? Or at least there's not the friction that you might be envisioning in your mind. It's not friction from the chain rubbing against the gears, okay? So when you press forward, okay, you're pushing forward, with this gear, okay, the front side of the gears in the back and the front side of the gears in the front, okay? So it's going to be this side of the gears, okay, is what's pulling the chain, which is then pulling these on their back side. I don't know what I just said a minute ago, but what I mean to say is it's pulling this way on these gears, and that's actually, I'm pushing the bike when I do that. So it's very clear that it's a very efficient system. So what you lose, and these are rough estimates from the past when I used to look this stuff up. These are rough estimates from my previous knowledge. In a bike like this one that I'm showing you right here, okay, even including the pulley wheels are what you call chain friction. All of the chain's friction is a certain unit. Maybe it's 10 watts, maybe it's 5 watts, maybe it's 20, I don't really know, but it's not that much, and that's solid. That's constant. Whenever you move it at all, that's it. That's the only one. I think it's about, it feels in this bike's case to be about 10 watts. Maybe less. I don't know. Maybe it's only 3 watts. I don't know. Maybe it's 3 or 4 watts. Who knows? Okay. I'll probably look it up. It's going to change from bike to bike. The more tension you have on the chain, like if I cause more tension on the chain, then there's going to be a little bit more. That didn't stick, but there's going to be a little bit more chain friction. Okay, but that's minimal, and most of the friction is going to be wherever the tensioner is. So this is using a derailleur for tension. So bikes that are using horizontal dropouts as a tensioner have a little bit more chain friction, and it's kind of difficult to balance that so that you don't have too much chain friction, so that you don't have an issue. Okay, so my single speed back here has to have a certain amount of tension to work, and you can see the sag in the chain there. You can see that sag from me pedaling backwards because it has a hub brake. You can see that sag, but you want just a little bit of sag in a single speed fixie. In a single speed or a fixie, you want a little bit of chain sag, but not so much that from bouncing around it might slip off the gear. So it's a little bit difficult to do without over tensioning, but you're talking about like 5 watts or less. It's not a percentage of your power, it's just a solid number, and it's fixed. Okay, it's a lot greater when you're using a drive shaft or internal hub gears. Okay, now if you used a single speed with a belt drive, it's actually going to be slightly less, barely less, if you have a single speed with a belt drive. Okay, maybe it's half the wattage. Okay, but it's less only if it's a single speed versus a chain to single speed. Okay, it's going to be a lot more if you have hub gears, because hub gears lose a ridiculous amount of efficiency, and it's not really that much, but it is a percentage, which gets me to point number 2. You are also having friction slow you down with your drivetrain, and that is a percentage of your power output. So 1000 watts is going to be, perhaps 50 watts, but when you're putting out 100 watts, you're only going to be putting out like 5 watts of friction. So it's basically going to be around 2%, really. So those are bad examples. So really 1000 watts would be about 20 watts of friction or so. That's going to be a percentage, because the more power you're putting out, the more contact friction you're having with the part in the chain that's in between. Okay, that little roller in there, that little spindle guy, he's gonna have more friction the harder you're pedaling. Okay, so 1,000 watts gonna be more friction than a couple 100 watts. Okay, bear that in mind, because that's important when you're sprinting, because that's one of those forces you have to overcome, and it makes sprinting a very exponential sport. Okay, 100 more watts doesn't mean the same for me as it does for somebody who's sprinting at 600 watts. Okay, because I sprint at over 1,000. So 100 more watts won't get me as much more speed as it will for someone who's sprinting at 600 watts. 6 to 700 watts is a huge difference. Okay, likewise, if somebody is a child or something and they're doing 300 watts, if they were able to do 100 more watts, that would be a huge difference. Okay, so don't forget about that. This is going to wind up being a little bit of a video series, so because I'm only on to drivetrain. So drivetrain friction, all right. There's chain friction, then there's friction that's exponential, or not exponential, but proportionate to the output. Okay, that's number one. Number two. Number three is going to be the resistance of your bearings and your wheels, which actually I've looked this up, and in a few sources, it has said that the friction of your bearings actually kind of acts like fluid friction, and because of that, it's exponential, which means from 0 to 20 miles per hour, you're going to have 1 unit of resistance, but from 20 to 40, you're not going to have 2 units, which would be linear. You're going to have maybe 3 units of resistance. And apparently the exponential curve usually doesn't come into play until you're going really like 40 to 60 miles an hour. That's where it really starts to, in an exponential curve, it's gonna go like this, okay, and then skyrocket. So you're gonna have, in the graph, you're gonna be going up slightly and slightly, and then when you hit the curve, okay, you're gonna curve real quick, and then you're gonna go really, really high, and that's how aerodynamic resistance works. But it's also how bearings resistance works. So your bearings are going to resist the wheel relatively lightly until you get up to like 60 miles an hour. Okay, that's part of rolling resistance. The more important rolling resistance, however, and I would say that bearings are only going to be around 10-20 watts until you get up to 100 miles an hour. Then you're going to be talking about 100 watts. That's why it's impressive that people can go like 160 watts, but it does depend on what kind. 160 miles per hour. That's why it depends on what kind of bearings you have, though. So anyways, this tire resistance with the ground is linear. That's a linear resistance. Okay, it's not a fixed number like the drivetrain. It's not like the chain, and it's not an exponential number like the gears, the friction on the gears, or the friction of air, or the friction of the bearings. It's a linear progression. So 10 miles per hour is 1 unit of resistance for the tires meaning the ground. That slows you down, okay? It's called rolling resistance. 10 to 20 miles per hour is 2 units. 20 to 30 miles per hour is 3 units. Okay, not a 3 unit increase, 3 units total. So there's 3 units of resistance at 30 miles per hour. There's 4 units of resistance at 40. There's 5 units of resistance at 50. There's 6 units at 60. This is important though, because it does go up. It's not some solid number that's maintaining itself the whole time. Okay, the faster you go, the more friction you have. Let's see if I can keep this all in one video. So, there's 2 kinds of rolling resistance, 2 kinds of drivetrain resistance. Alright, there's also negligible resistance in the bearings of your pedals and your crank, but it's pretty negligible unless there's something wrong. Okay, that we're not going to include that. We're not going to include brakes or anything else. I'm going to take one other video to explain a little bit about how aerodynamic resistance works. Aerodynamic resistance is the biggest one, and it is exponential. Alright? Which means 1 unit for 10, 3 units for 20, 5 units for 30. Alright? and so on.